Hi, I'm Anubhav and this is the final video for the Science 2 project. Now this project was divided into two phases. This is the report for phase 1 and this is the report for phase 2. In phase 1, what we needed to do was to use SMD and simulate the trajectories of molecules and make a GIF file out of it. Whereas in phase 2, what we needed to do was we needed to perform calculations to find out potential mean force, also known as PMF, and understand and verify the Jarzynki's equality. Jarzynki's equality formula. Jarzynki's equality formula gives the relationship between free energy, which is F, and the work done in a system. This is the expression for Jarzynki's equality, and it is given by e power change minus the change in free energy divided by T, where T is temperature times Boltzmann constant, and it is equal to e power minus W by T. It can also be rewritten as this expression over here, which is f of c of t minus f of c of 0, which is change in free energy, and that is equal to minus t times log of e power minus wt by t. This is called the exponential average. The wt term is the first cumulant, and wt minus half t times wt square minus wt average of wt square minus average of wt whole square is called the second cumulant. They are approximations of change in free energy. Delta F equal to W for reversible work. We also have something called Jensen's inequality, which is delta F is less than work done. Out change in free energy, the output change in free energy is path independent. Now let's go through the details of the SMD run. So let's look at phase 1 first. In phase 1, what we had to do was first download the protein and then download some other important files which we were given to use. And by uploading it to Charm GUI, we get all the new parameter files. Using the parameter files and using NAMD2, we get da underscore smd underscore tcl.out, which is the output file that shows the trajectory. da underscore smd.dcd is one of the main files which we give argument to VMD with, and we have to make a GIF file from the output of the VMD. Next comes phase 2. Here we need to calculate the PMF. The files used for the PMF calculation and the link to the video will be updated after making the video. Here we consider a very small time velocity so that we can see Jarzynki's equality in action and say that work done equal to change in free energy, nearly equal to free energy in this case, at reversible or quasi-static processes. So we increase the time step from 200 to 2000 picoseconds so that the terminal atoms Z go from 13 to 33. Then we plot some graphs. Instead of single trajectory, we generate 3. Some helper scripts were already provided to us, and we use them to plot extension versus time graph and force versus extension graphs. Some parameters need to be modified to work in our case. For this to work in our case, load trajectory takes in da.dat file, and all the steps necessary to generate the graphs are provided here. So these are the kind of graphs that I get. The molecule that I was assigned is 2KIT underscore A. My understanding from these results are that it clearly shows how simulations work. And this particular graph, it's not really a straight line, but it's jagged. Even the force extension graph isn't a straight line. It constantly increases and decreases. These are the PMF graphs. F-exp is almost equal to F1 here, as the scale here is quite small. But when we bring in F2 into the picture, F2 becomes very negative, as we are expanding only to two terms. Some graphs of other people are also provided. These graphs were obtained from the molecule 2 underscore A, and here also it's not a straight line but quite jagged, and here it increases and decreases. Another result, another set of results is obtained on 4J underscore C. So what we see from these graphs is that they are quite similar but they are not exactly the same, and this is because different molecules are used. Next we'll do a comparison between the three molecules. Extension versus time step. All our graphs, mine, Meg's and Tirth's, were constructed using initial point at 13 and velocity of 0.01 angstrom per picosecond. We ran our simulations for 200 picoseconds by taking the respective atom from 13 to 33 angstrom. Atom final position was about 88A. As is evident, the graph does not follow straight line but does not deviate much if you draw a straight line for trajectory. Force versus extension. Initial part of the graph do not have anything, as the extension starts from 13A. Force do not follow any type of particular pattern. Graphs can be compared using the range of force shown by each graph. These are the different forces in different molecules. This is the minimum force and this is the maximum force. They correspond to the lowest Y value and the highest Y value in the force versus extension graph. PMF. Every one of us used Jarzynski equality for finding PMF values and plotted the graphs. For each of us, F2 went below zero line, while the other two, which are Fexp and F1, are above zero line, which is the x-axis. The results were similar between all the three molecules I used. Jensen's inequality can also be verified using PMF graphs, which is Jensen's inequality is free energy less than work done on system. It is observed in the three studies that F1 and Fexp increase whereas F2 decreases at a much larger rate. The effect of velocity. In the SMD simulation, the effect of velocity is that if you have small velocity, it becomes reversible work. For movement at very small velocity, it is possible to infer that change in free energy is equal to change in work done. If velocity is further decreased, the free energy becomes much lesser than work done, which is a direct extension of Jensen's inequality. With increase in velocity, the work done increases as well as the PMF increases.